Hey everybody, this is Larry. This is day 24 of the Leetcode Daily uh, Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's poem and just life in general. Um, Sometimes I use these things as like a little bit of a vlog. I want to say that it's been a really rough day for me. Not, I mean, I do these things as a hobby, so it's fun for me in general. I didn't do that well on the competitive side, but I don't care about it. Um, just real life sometimes happens and it's been a little bit rough, but anyway, all that said, I'm okay. So yeah, thank you for whatever watching and all that stuff. Hope y'all taking care of people you love in your life. Anyway, so today's poem is merge case sorted list. You're given a k linked list of lists. Each linked list is sorted in ascending order. Okay, so you have lists, you have sorted, and you want to merge them into one sorted list. So this is a very canonical merge sort type thing, in with multiple lists, and there are a couple of ways you can do it, for sure. And yeah, however you want to do it is probably fine. Depends on the k, and as long as you're able to analyze and kind of, if you're on in if you're on an interview, be able to talk consistently about your experience and just trade-offs and how to kind of go for other solutions, and what the complexity of those things are. You could probably do that. So yeah, so there are a couple of ways to do it. As I said, there's like a divide and conquer merge sort type thing where you take half the list, you merge them. You take the other half of the list, you merge those, and then you build your excuse me. As I'm saying, I do record all these live. I am, especially by today, I don't have the energy to edit it out. But yeah, so then you basically is just merge sort. So you take half the list, you take the other half of the list, you merge them and into one list, and then recursively you do that. So it's way divide and conquer. That's one way to do it. Another way to do it, for example, is just using heap sort. So basically you get the min element, and then for every min element you pop it off, and then you get the next element on the list. I think those are the two big ones that I would consider, mostly because those are the ones that are, I want to say, they're optimal. We could analyze it later, but those are the two ones that are like log e. Like they have some logarithmic factor in the complexity, which is better, because any other, maybe there are other ways, but if you do some, like, if you have to go through the list every time, then it becomes too slow, right? So those are the things that I would say. Yeah, and there are a lot of lists. There are many lists, and yeah. Oh, actually, but each length is not that bad. Okay. By the way, so yeah, let's get started. As I always say, for these kind of linked list forms, I always just have just have a head node, so that at the very end I return the head dot next. And then for this one, I'm going to do heap sort, just because it feels easier to write in a way that is harder to do off by ones, because when I do if I'm doing this in a competitive kind of way, and I do merge sort, divide and conquer, I will always have to kind of figure out, like, okay, what happens with the off by ones. Maybe not so much, but that would be in the back of my mind. That's what I'm thinking now. But with heap sort, I don't think I have to worry about it at all. You just kind of dump everything in a heap, and that's fine, right? So yeah, so we have a list of nodes, so let's kind of put the first item all in a heap. So I have a heap. If you're not in Python, one thing that I would say is that Python heaps are min heaps, where in other languages they're often max heaps. So you might have to play around to get that right, or overload the computer or something like that, depending on where you go. So yeah, so so let's call list heads. In lists, we pushed it to the heap. Also the heap syntax is a little bit funky, but so we want to push the first element. Let's just say list head. I guess list head is the first element, and the key, or the priority of the heap being list head dot that value, I think, yeah. And that's pretty much all. And yeah, as I said, this code is way, as long as you remember that this is a min heap, this is way, like, there are very few places to make errors, or if you do make, even if you make an error in the min heap, you just go, you do a negative or something like that, right? So that's fine. And then now we do a while length of heap is greater than 0. Yeah, and then we have a tail. Actually, tail is equal to head. Yeah, I actually should have done that actually, but it's fine, right? I mean, sometimes you don't always implement everything in the thing, because I'm not prepared per se. Like, I do these live, right? But yeah, so while the heap item is greater than 0, we want to get the first item off the list, so we just have a value, and then we have the head, or let's call list head again, is equal to heap sub 0, and then we pop it, right? And then now we process this thing. We actually don't care about the value. You could do this in 2 ways, right? You could do something like tail.next is equal to new, with the value, but I think in this case, we want to, just for a space purpose. Actually, let me think. I don't know. It could be yeah, I mean, I think it depends on what you mean, because I think usually I hate doing things in place, because usually for most functions it doesn't make sense to do them in place, because it's like, oh yeah, get the 5th item, and then you have to like mess up everything on the array or something like that, and it's like, as an API caller, people be like, why did you mess up my array, right? But for this particular function, because it is merge k list, it probably is a reasonable expectation to merge it in place. So so I'm going to do that. Otherwise, this is the way that you would do it, not in place. And then, you do something like tail is equal to tail.next and something like that. But here, we can actually look at it directly. We could set tail .next is equal to list head, and then here the thing that we have to be careful now is to add the next item on the heap. So now heap push heap, we do okay, so that's yeah, tail is equal, is this true? Oh yeah, this is fine. But we're modifying tail.head. So yeah, with linked list, if you have any issues with kind of visualization, feel free to draw it along with your code, because these are a lot of pointers manipulation. But yeah, if list head.next is not none, then we want to push the next item, which is I was going to put something like, okay, fine, let's do next node is equal to this head.next, and then you have next node dot value, and then next node itself, and that's mostly it. I think the only thing that's left is that we set list dot next is equal to none. This way we don't have any dangling well, actually, we want to do this in any case, just so that we don't have any dangling pointers. And then when we set the tail to tail.next, which means that tail is now equal to list head, yeah, this should be okay. I think this should be good. As I said, these things kind of is a little bit tricky, so let's double so I'm not super confident, but this looks okay. Feels okay. Let's see. Okay. What? Oh, that makes sense. Actually, I didn't anticipate this. Huh. That is annoying. Because basically what I want is this to just be a pointer that we don't do a comparison on. But because it's a tiebreaker, right? So let me, because I just want it to be an item that's almost like a pointer to the item, so we don't have to worry about it. But let me see real quick. Non-comparison. I actually don't know how heapq handles it in Python, so this is new to me. So let me take a quick look. I'm just looking at the heap queue API right now. If you're wondering, um, hmm, heap pointer. I just want something that holds a value but doesn't um, that we don't have to compare on. So this is actually annoying. Let me think about this. Actually, I didn't anticipate this as part of the implementation. So mistakes were maybe made. Um, hmm. Tuple no compare. Maybe we just have to write a custom thing. Eh. Okay, I googled this and I found something like this. Maybe this is good enough. Um, and it actually is very close to I don't know, by coincidence. This is very copy and pasteable. I don't. Maybe someone is doing Leetcode stuff. But yeah, but let's give it a run just to kind of see. I'm curious now. None type has no attribute value. That's fair. Uh, hmm. Uh, Let's see. Wait, why is that? I thought this should be none. Did I messed up somewhere? Oh, this could be a none. Okay, so that's fine. I could just fix if this head is not none. Because I think for this one, it just means that the head element is a none list. So yeah, okay. So this looks mostly good. I definitely do not recommend this. But I think the rest of the abstraction is okay. So let's give it a submit just to kind of see. Maybe I have some mistakes before I, okay, cool. Yeah, I just want to make sure that I'm right before we explain it. But yeah, but this is just heap. This is actually way, I want to say, ooh, what did I click on? Like this isn't like in, this is one of the textbook E solutions. I'm just trying to see if there's any, okay. But yeah, but basically we actually just want a pointer and, so when we overload this, it just makes some comparison, but it doesn't. It's like a tiebreaker for if this is equal. That's why we kind of need it. And it's okay for them to be equal, so that's why it doesn't really matter. But yeah. So basically, for here, we convert this to a tuple. We could actually have wrapped this around, because now that we have this, we actually could just do the pointers themselves. So actually let's do that, because usually this is the tuple is a little bit of a, I wouldn't say a hack, but to kind of put the key, but now we just do the sorting directly. So let's actually run the code real quick to see that it runs. Whoops. Oh yeah, because this is no longer a thing, because we don't care about the value anyway. We never used it. Okay. Yeah, okay, so this is a little bit cleaner, even though this part is very yucky. So I'm gonna write, don't try this at home. Write your own wrapper class. So yeah, so what I would do in theory, if I was in, if I have more time and infinite time and prepare this already in front of you, I would have wrote like Larry node or something like that. Larry's list node or something like that with this compare this less than function, so that we can do a comparison and then we put it on a heap. Yeah, so I have the first item. I keep track of the tail. I put all the heads on the heap where it is sorted by the value. Again, this is a min heap, and then we pop them off one at a time. And when we pop things off, we just push the next item on the heap. And that's pretty much all I have for this one. What's the complexity of this, as you may ask? Given k lists, this will be, the heap will have at most k items at any given time. So each operation is going to be log k. and that is an invariant because every time we pop an item, we add another item from that list, and so that only gets smaller. So it is log k, and the worst case is that we all have you know yeah, for n items, for each of those items we do log k operations. So at worst this is going to be n log k, or yeah. So that's the time complexity. The space complexity, obviously, we just we only put things in a heap. So at worst, this is going to be O of k for space. But yeah, I think for upsolving, definitely practice using the merge sort recursive divide and conquer as well. Trying to figure out the complexity there. Let me know in the comments how what's the complexity, and I'll check it out for you. Yeah, that's all I have for today. Let me know what's going on, and I will see you tomorrow. Bye bye.